Hello and welcome to the wolfSSL live webinar, Automotive Security, uh, with our wolfSSL engineer, Jacob. My name is Marcos. I'll be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please submit them using the Q&A box. We'll be answering them after the presentation. I invite you to follow us on Twitter at wolfSSL as well as our other socials. Also, feel free to email us at facts@wolfSSL.com if you have any additional questions. Before we get into the presentation, I'm going to give a brief company overview. wolfSSL was founded in 2004 by Todd Oska and Larry Stefanik when they realized there was an open source, dual license embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2023, most of which are engineers. This progress, of course, is supported by a strong partner network that we're proud of, which includes CTCI, STMicro, and RTI. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification and FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for Grill. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. That's all for me, so I'm going to hand it over to Jacob now to get started with the presentation. Thank you.
All right, thanks. So we secure over 2 billion connections, and we've been in the automotive industry for over 15 years. So one of our first companies that we were working with was actually in the automotive industry. There are three main areas that wolfSSL focuses on, all dealing with securing your data. The first area being data in transit, and this is done with protocols like TLS and SSH. They allow for data integrity, authentication, and encryption when sending and receiving information. The second area of focus is data at rest. We have our crypto library that supports progressive ciphers as well as the well-known standard algorithms. This can be used to encrypt data at rest. The third focus is providing software that assists with firmware updates. This being our MQTT implementation or through use of TLS also. And having a secure mechanism for firmware updates helps reduce the risk of malicious software or malicious firmware being introduced. Going over some of our products that are typically used in the automotive industry. A lot of automotive projects have involved wolfSSL use, which is our flagship TLS implementation, making use of the tried and true wolfCrypt library for crypto operations. Other projects that we have done for automotive companies involved wolfSSH being used on test rigs and firmware updates. And one of our latest software products, wolfSentry, is also a nice fit in embedded use cases for intrusion detection and prevention with automotive. And then you'll see down here on the bottom, we have the Swiss Army knife of URL tools, curl. It's another product that sees frequent use in the automotive industries. It is used on basically every infotainment system out there on the road. And we have support packages available for use with curl and a recent tiny curl build for a slimmed down version of that can fit into more resource constrained devices. Another one of note is Wolf Engine, which provides a solution to plug into OpenSSL. So OpenSSL is doing the end of life with 1.1.1. If you want to update it and maintain crypto, you can come to us for that Wolf Engine plugin. If unable to change the application's code to make use of wolfSSL native API. And later on in this presentation, I will be going through some more specifics about projects that we have done in the past with automotive and the parts that have been used with them. So wolfSSL has a long history with use in automotive systems. The company has, as I mentioned, 15 plus years of experience working with and developing for automotive companies. One of the first companies we worked with was General Motors. And since then, we have expanded to be in 3 out of the top 5 auto vendors, with major customers in Japan, Germany, USA, and France, so not limited to just USA products. wolfSSL products are used in a broad range of applications. This could be anywhere from the ECUs to telematics to infotainment systems. And with the reliability and support that we provide, 2 of the world's biggest auto vendors have actually standardized on us. And this means that anytime that they're looking for some kind of crypto operation, they come to us. Often when thinking about cybersecurity with automotive use, the first group of vehicles that may come to mind are the military. We are not just used in military or luxury cars though, but are used throughout the whole industry. For example, we are used in vehicles with agriculture, many infotainment systems on vehicles on the road, and mapping and telematics with driving assisted systems and back-end servers to process automotive connections, all the way to commercial trucks used to haul freight. There are many more use cases, but this gives a good example of the wide range of applications wolfSSL is used in with the automotive industry. The first project I'll be talking a little more about in detail was a vehicle-to-vehicle use case. With the increase in car connectivity, it becomes useful for vehicles to share information with each other. And this can be helpful in many ways, but not everyone the vehicle connects with may have good intentions. Solving this issue requires authentication of who's being connected to, but also requires that authentication to happen quickly in order to diminish the user experience, not diminish the user experience, and to keep up with how fast things are happening on the road. In the project for the aforementioned vehicle-to-vehicle use, we leverage the DSP, which is a digital signal processor, to get the most that we could out of the hardware being used. This helped in multiple ways. One of them being that the crypto operations could then be offloaded, freeing up the main CPU for other operations. It also helped in high volume cases by being able to run more verifications operations in parallel. In this case, we were targeting around 16,000 verifications per second. This is ECC NIST P256 verifications per second. And we have a lot of alternate hardware offloads that we support with wolfSSL. One of the later ones we'll go into is CAM as well, which is an XP offload. The main crypto library wolfcrypt was used for signature verification, and to help with the performance requirements, it was built with the SP math. SP is a single precision implementation that my coworker Sean developed for commonly used key sizes with some asymmetric key algorithms. And this SP math was extended to be used on the DSPs available, along with potential caching for performance enhancements when verifying using the same key multiple times, same private key multiple times in a row. Another part of the use case was a custom library built for dispatching verification operations. This code assisted by handling receiving a verification request and directing which processor the verification should be done on. For this case, we also implemented SM2 in order to be used in the Chinese market. This implementation is not in our main branch or release bundle, but is something that we have available if needed in a project. That's the SM2 implementation. So we have a separate repository up on GitHub for that. If you contact us, we can get the SM2 implementations too. In addition to SM2, it had Brainpool for some of the European market, and then also the NIST implementations for here in the US. One of the big hurdles for engineering in this project was the communication between the cores, passing cached information for performance enhancement from one core to the next that would then do the verification operation. The data has to be serialized in a generic way, or either the code on both cores compiled to expect the same size of data types. The project called for a lot of optimizations and performance enhancements. One performance enhancement, for example, was adding Brainpool and SM2 support to the SP math. Another investigation to potential performance enhancements was done with the HVX, which handles operations with large vectors very quickly. Throughout the development, many benchmark collections were made to investigate the trade-off of number of threads being ran in parallelism versus the point where the task switching between the threads affected the performance negatively. Another thing that we did with this project was testing of the isolation of processing power to a single core. This was with the dispatcher code to make sure that it was offloading it to the core that we thought it would be offloading it to, and not taxing any of the other cores. Next project that I'll be going a little bit more in depth about was a secure firmware update project. Part of the use case on this was retrieving and authenticating new firmware updates. It would phone in to a backend server, making use of wolfSSL and curl. And one of the things we did in this project was have a heightened security using CAM from NXP on an IMX device, specifically an IMX6 device. And the CAM driver that we added for this project supports both hardware encryption and secure key storage on QNX. And that more specifically was a QNX resource manager that now comes bundled with wolfSSL. Some of the products involved was curl, wolfSSL, making use of wolfcrypt, and it was integrated with the CAM driver for key storage and retrieval to be able to use black keys, black encrypted keys. A little bit into the specifics on the engineering details. So leverage the IMX6 device and vastly improved security. This was made possible by using the encrypted black keys. And in addition to using the encrypted black keys, it was encrypting them with AES CCM. So NXP has two different modes. It has AES ECB, which just does the simple AES encryption of the key using the key encryption key, but it doesn't include a MAC. AES CCM, which was used in this project, also has the MAC at the end to authenticate to the integrity of the encrypted key. And the use of black encrypted keys was with the ECC ephemeral keys created during a TLS connection, as well as just the private keys as well, for verifying certificates. And then it also had red and black blobs. A blob in this particular case is NXP's storage mechanism. So a red version of it is the unencrypted version of the blob, and then the black blob takes in a black key and prepares it in such a way that it can store it as a blob. And the problem that the blobs solve is if you were to do a power cycle with the device, that black encrypted ECC key that was created earlier would then no longer be able to be used after a power cycle, just because the key encryption key is going to be changing after a power cycle. So with a black blob, you're able to store a black key throughout a power cycle, and then load it in afterwards and continue to use that private key. This was running on QNX. We worked with QNX 7.0 and 7.1 with this project. We've done other versions of the QNX operating system too. QNX 6.6 comes to mind. So we've tested on quite a few QNX versions. And the performance with the sign and verify with the black encrypted keys was close to an optimized unencrypted operation. So on this table, on the far right-hand side, we have the single precision assembly version, and the average milliseconds for each of these operations versus in the center here, these are the making use of the CAM with black encrypted keys. And then on the left side here, we have the software only in comparison. So the biggest one that's going to be impacted by the encrypted keys is the sign operation because it's using the private key there. And then agree would be as well, but the private is just going to be using the unencrypted public key. Another project that wolfSSL is used in for automotive use is with a TLS connection from the car to a backend server. This includes the option of using the most recent TLS protocol, TLS 1.3. In this project, it was a relatively complex network setup involving both wolfSSL's TLS and MQTT implementations. For those that may not know, MQTT is a publisher subscriber protocol, which can be used for mass updates or just for sending info to many subscribers at once on a network with varying times of when the device is connecting or potentially reconnecting. An example of a potential use case that Wolf MQTT could be used with would be sending road conditions to all subscribers in a specific city or weather updates. The device would communicate through the secure connection using a proxy setup with a backend server. The main wolfSSL products used in the project were wolfSSL, Wolf MQTT, and curl. Curl is commonly used in automotive combined with other wolfSSL products. Daniel Steinberg, the author of curl, he works here with wolfSSL, and we have support packages and consulting offered, which helps streamline the experience of integrating the libraries into an automotive application. You'll see curl used quite frequently throughout all of the automotive industry. No major consulting was done with this project. Most of the engineering effort was around supporting integration and assisting with resolving any issues that came up. With Wolf MQTT, the project was using the V5 implementation and multi-threading. For use in the project, some multi-threading with Wolf MQTT was expanded upon. Another one that wolfSSL has been used with is autonomous driving software. The automotive industry has been progressing towards fully autonomous vehicles, and the need for security with communications and critical system operations when a heavy vehicle is controlling itself down the highway is pretty paramount. In the software application, wolfSSL was used for connection to the server for map updates. The connection to the server for map updates assisted with navigation. This up-to-date map setup for navigating through roadways was used in an advanced version of cruise control that assisted not only with maintaining speed, but also with maintaining position on the road. You can see why it's pretty important to have your location be secure. You wouldn't want necessarily everyone to know every spot that you're visiting when you try to go get a map update. And that's also important that you get the correct map updates that have been authenticated from the backend server so that you're not being directed to a location that you don't necessarily want to go to. wolfSSL products used in the setup were the main wolfSSL library with TLS 1.3. This was also used with one of the many automotive OSs that we support, Green Hills. For security reasons and to fulfill the industry requirements, Many of these automotive projects we work with are using either QNX or Green Hills for the operating system. And we fully support both of those operating systems, along with other potential operating environments. In some cases, we may say like a bare metal microcontrollers for one of the edge devices. And we can build wolfSSL all the way down to that bare metal running environment. A few of the engineering specific details about this project was the porting work done to run on a ST Telemaco board. Porting a new system often requires setting up the hardware source of entropy if available, handling any mutex uses if using a multi-threaded build, setting the types correctly for the hardware along with other small modifications. We do have a porting guide, so someone could go through this porting process on their own. We try to make wolfSSL as portable as possible with the tie-ins for any system calls abstracted. Lots of times someone will come to us to the port just because it's a lot faster and more economical. Usually we can get a port done in less than a week. Whereas if they were to get up to speed and do it themselves, it takes them a little bit longer. In this case, we also made use of hardware acceleration. The CPU being an A7, it could use our existing ARM assembly accelerations in addition to what hardware acceleration was available on the board. Some MISR-C effort was done with specific wolfcrypt source files on this project. Most cases we have found that MISR-C is not a hard requirement in the end, which was the case here as well. A lot of automotive projects, they require static analysis reports to be compliant with industry requirements. These static analysis reports, though, do not have to be MISR-C, only a static analysis report of some kind. So often we can run, say, like a covariety for a static analysis, or even one of Kling's static analysis reports to satisfy that requirement. Another automotive specific use case that we support is NTP for AutoSAR, which is a network time protocol. It gives a way to have secure time stamping for events for smart cars. Some of the examples of use cases where this is critical is with brakes having the same time reference as any machine vision systems. It's not a good thing if your brakes are too slow. It's also not very convenient if your brakes are too fast in comparison to what your machine vision system on the car is picking up on the road. And our NTP is maintaining a constant sub-millisecond time in the vehicle. It's also cryptographically secure for the reference of time. And this means that someone can be tampering with it to try and trigger your brakes sooner than what you would want or later. It's a critical but simple facility. And why do we need NTP on a car? I went over with the critical systems like the brake, but also synchronization of subsystems in the smart car. And this could be also like just convenience synchronizing with a smart device connecting to the car. It also can be used with forensic reconstruction of events. If something did ever happen, such as like a crash, you'd be able to go back through the log and have a timestamp mapping up to the events leading up to it. wolfSentry, one of the relatively newer products that I called out, fits well into the automotive industry. wolfSentry is used to identify and mitigate network intrusions. It has a filtering. It can be used for filtering bus traffic. It can also be plugged in to have specific actions that it does on events. It's very configurable. We also have a way to be able to dynamically respond to a block of bus spam. So it can detect something like someone spamming a bus. And it has full LWIPS support. It can be tied into basically any type of medium. So you could potentially tie this into the CAN bus as well. wolfSentry was designed for embedded devices. It's a good fit on resource constrained devices as dynamic rule generation and transactional rule changes on the fly. It makes use of JSON files so you can update the rules as needed, and it's able to take those updated rules and just run with them. It also has the ability to record and react to events. Something else that helps with the ISO 21434 is just wolfSSL in general, which is securing the transmission of event data. So I say wolfSSL, this means like the implementation we have of TLS, which also secures general communications between microcontrollers and servers. And then another product that helps with the ISO 21434 is wolfboot, which allows for the secure firmware updates. Something else that we support that helps with the automotive industry is TLS over CAN. It was in the news recently about a lot of CAN bus attacks and thefts that were happening with vehicles. One of the notable cases was they would come in through the headlight connection, attacking the CAN bus, and not necessarily need to have like a spoofed key fob or anything or gain access to the inside of the vehicle, just a simple panel pulled back and access to the headlight, and then they're able to steal the car. And almost every part of the car is getting connected via the CAN bus. One mitigation that would have helped out to avoid this attack would be using TLS across that connection. Most of those CAN connections at the moment are just unsecure and in plain. So CAN stands for the controller area network. Something that the TLS offers when ran over the CAN bus is authentication, encryption, and integrity. CAN is used in the top industry standard for intra-car security. So this is all of the stuff talking to each other inside of the car, not necessarily anything phoning out. So how did we implement this in practice? We use the ISO-TP wrapper with a variable minimum packet delay. People familiar with the CAN bus will know that it has a very small packet size, just 8 bytes. This ISO-TP wrapper allowed for expanding that to 8-byte packet, or handling that 8-byte packet size to be able to then send TLS packets across it. And we have it adaptable for the CAN FT if needed. In the implementation that we did, we targeted TLS 1.3. This was for the reduced round trip handshakes sizes, so it just had less communication going back and forth with the more state-of-the-art TLS protocol. And we had a simple callback interface that also, with our CAN TLS over CAN bus implementation, so it's pretty platform agnostic as far as which CAN bus is going to be running on. So you have the diesel version and then the gasoline version as well. Yeah, wolfSSL, we do a lot with testing. We test in order to avoid crashes, be that crashes in the software or leading up to crashes in the vehicle. We try and avoid those, and also just to improve the quality of the code. So a few of the testing that we do that's related to the automotive industry is we have benchmark tests on real hardware, multiple boards that are running. So it keeps track of the code size versus, we also keep track of code size versus boot time, measure memory resources, and manually run additional resource collection to update usage figures. Then we have some functional tests running on the real STM32F4. And this is all related here to our wolfboot product. So it covers the forward update and rollback with wolfboot SPI flash tests. And we also do some with like the TPM testing. Some cases they may need a TPM for the private key, and then testing with combinations of possible DSA plus SHA algorithms with wolfboot. For testing with our main wolfSSL library, we have what we call our rainbow of testing. When we're adding new test cases, we tend to focus a little bit more on the center, and then we expand out from there. So you have the API tests and unit tests as the core there, then the peer reviews. Any code that's getting merged into our master branch goes through a peer review. And this is regardless of if it's an automotive use case or not. It's just all code that gets merged in has to go through a peer review before it gets merged in. Then static continuous integration tests with static analysis, memory leak checks, interoperability tests, and Cipher Suite and certificate tests. We also do some regression testing, a lot of build option tests, product testing. We also do OS tests, make sure it runs on different OS tests, some hardware acceleration tests, different compilers. Then we're dual licensed and being an open source product as well as commercial, we have the open source community that takes a look at the wolfSSL library, actually all of our libraries that are open source. And we'll get cases where universities have done research projects on it, or other labs have taken a look at it. And then we have some third-party testing as well. We're plugged into like the OSS flows, for example. Some benchmark testing, wrapper tests, and then on the edge of our rainbow of testing and some of the potentially new tests that we may add. That covers a few of the projects that we've done in automotive and more in depth. Some of the engineering hurdles that we overcame with those projects, and a little bit about our use case in automotive. And at this time, I'll go ahead and open it up if there's any questions that people may have.
All right, awesome. Yeah, we have a couple questions queued up. First one is, does wolfSSL have support for ED25519 signatures? Also, has this been used in any of the automotive devices?
We have support for it. If it's been used in automotive, I'm not sure if it has or not. So yes, for support. And off the top of my head, I don't know if it's been used in an automotive use case.
All right, awesome. Next question, have you tried TLS over CAN?
Yeah, we have a TLS 1.3 over the CAN bus.
All right, awesome.
And if you're looking for where to access that, I believe it's one of our repositories up on GitHub, one of our public repositories. If you'd like more information about it, though, go ahead and contact us at the FAQSat, and we can get you exact link and walk through the build step and use of it.
Yeah. Oh, also a reminder, if you prefer to ask your question verbally, you can click the raise hand button. We can unmute you so you can ask your question that way. That was all the questions we had queued up. We can give it a minute if anyone has any more questions. Okay, here we got another question. Will the Chinese SM ciphers be open sourced and available as GPL?
Yeah, that's an ongoing dialogue that we have internally. I think right now we're just keeping them as a separate private repository. We don't have a time frame for when they'll be released as like a GPL open source.
How much of what was covered today is open source versus the enterprise version?
Sure. So I'd say 95 to 99% of what was covered today is open source. The only thing that really isn't in the main repository is just the SM2. algorithm that was mentioned, implementation that was mentioned. But yeah, all of that CAM stuff with the QNX resource manager, that's in our main repository. And then yeah, wolfSentry is up in our main repository, up in a public repository, separate. So most of it's up there in just our main GitHub repository or on our download page.
Awesome. And Edward has his hand raised, so Edward, you should be able to unmute yourself. Yeah.
You hear me now?
Yeah, I can hear you.
Okay, so one of the big things I'm seeing is that car networks are going to zonal architectures pretty quickly with Ethernet, T1S, and all the rest of it, because just they've come to the conclusion that CAN's got severe restrictions and speed and latency, et cetera, et cetera. So what are you seeing and what are you planning to actually go in the Ethernet support direction?
So we wouldn't have much difficulty going with the Ethernet. The wolfSSL, it's pretty agnostic as far as what medium it's running across.
Yeah, I would think so. I just wanted to check and see what you're starting to hear from your customers. Like, is this something they're considering? Because some of mine, I see it happening pretty quick. So.
Sure. Yeah, I haven't been involved with any specific project working on the Ethernet instead of a CAN bus. Most of the stuff that I've been involved in is like the hardware acceleration tie-in or porting to a new device. But yeah, where it's, so I can't say for sure if I have a good feel on where our clients are going to the Ethernet or not versus the CAN bus.
Yeah, I'm starting to see tier 2s and tier 1s getting specifications from the OEMs on 1, 2, and I always get the numbers screwed up. The cybersecurity for Ethernet spec, right? Doing your working documents, and that's coming real quick as well. So your products will help in that area greatly.
Yeah, that's a good note, and yeah, that sounds like a good improvement over the CAN bus.
All right, thanks.
All right, thank you, Edward. All right, we have another question that came in. Is there a PKCS number 11 library available for Wolf TPM package?
For Wolf TPM, I'm not sure. We do have a PKCS 11 a repository, so we have some PKCS 11 support. I'm just not sure off the top of my head if it's been tied into the Wolf TPM library that we have. That's one that we could get you more detail on if you contact us through like Vax at wolfSSL. We can go into the use with PKCS 11 with Wolf TPM.
Right, awesome. All right, so that was all the questions we had. We can give it a couple seconds before we call it. But yeah, like Jacob said, if you have any follow-up questions, just go ahead and email Vax at wolfSSL. But yeah, it seems like that's all the questions. So thank you guys for joining. Thank you, Jacob, for the awesome presentation.
Yeah, thanks everyone. Thanks for the great questions at the end.
All right, yeah. I think we'll end it here. Hope everyone enjoys the rest of the week.